Hello, I'm Rohan with my partner Sai. I worked on this project on emotional AI, or emotion analysis with context. So the general summary of our project is that the problem we are trying to address is that emotion analysis is an important problem for lots of machine learning tests, and it is as yet unsolved. There's room for improvement. Our goal was to find a neural network design and specific improvements to neural network designs that can enable appropriate assignment of emotions to various text inputs. Our approach here was to generate some custom data sets for our experiment, then to use an architecture that includes glove word embeddings and LSTM layers to experiment with a few different things, including whether or not context is useful for improving performance on emotion analysis tasks. And finally, we want to determine the best hyperparameters for performing this task with this architecture. The general takeaways were that for the no context dataset, the best hyperparameters were the optimizer of n atom and a batch size of 64. And then for the labeled context dataset, using an LSTM-based model and an input that included the context worked best. And more details on this will, of course, come later. The basic motivation here is that emotion analysis is a useful task for any context where an autonomous machine learning agent interacts with a human, because frequently these interactions, the best way to perform them will include an understanding of what the human's emotional state is. And a chatbot is an example of this, where the responses should rely on the emotion of the human. So some background work related to this includes sentiment analysis. There's lots of work related to this that we leveraged. And so I included a survey that we looked at to try and better understand previous work. Emotion cause pair extraction is a specific example of this that looked at ways to identify specific words in sentences that are paired with certain emotions that cause them to be present. Then for word representations and natural language processing in general, we utilized the global vectors or glove embedding. And then we also had to look into LSTMs and skip connections generally as useful tools to experiment with for these tasks. So some of the technical challenges that we faced, including the need to customize data sets, because there wasn't a lot available that we could find that allowed us to compare between examples with no context and with labeled context. Again, I'll explain that further in a little bit. We did also have to find some existing data sets that we wanted to adapt for this test, just to allow that we could experiment and test on more examples. Then we had to design neural network architectures that would work for emotion analysis, perform hyperparameter searches in order to figure out what is most effective. We need to find good NLP word representations, which again utilized glove. And we wanted to find ways to leverage context. So context essentially refers to what is the sentence topic or theme. So an example could be the context of a sentence is about food or about a location and things like this. So we had to develop a data set that allowed us to, two data sets that allowed us to look at what's happening when there is context, specific context versus not, and when a loss function is actually related to the use of context. So some more details are here. On the left side is a no context data set where essentially there's not much to look at there because there's no specific topics that all of the phrases or questions are related to. Instead, they're all just labeled with a number, and they go from 0 to 5, each of 0 to 4, each of which represents a different emotion. So those would be angry, anxious, happy, sad, and confident. On the right side is a labeled context data set where there are specific topics, and each of the classes is a different emotion context pair. So, for example, many of these relate to locations, and so that's an example of context, and there are the same 5 emotions. So in total, the two contexts are either locations or food. And so in total, there were 10 different classes in this data set. So I'll talk about the no context data sets, and Sai will talk about the labeled context data set. So the architecture that we used here is shown. I just showed the Keras layers that we called. So we first developed an embeddings layer, which utilized Glove, as I described earlier. And then we had two LSTM layers that used dropout during training and a dense layer at the end with a softmax activation for multi-class labeling. So then we performed hyperparameter search that went through various optimizers such as NADM, ADAM, RMS prop, and ADA delta, and also various batch sizes from 8 to 64. And as you can see, it's sorted by test accuracy. So at the top, there are a few that had the same test accuracy, but the one that had the best test accuracy and time to train was using NADM with a batch size of 64. On the right, you can see some of the plots for the training progress. And this shows, as you can see on the top left, there's improving training accuracy over the course of training. On the bottom left, there's decreasing training loss. On the right side of the validation training accuracy and loss, which fluctuate more, but generally follow similar trends, but yeah, don't converge in the same way, of course. Yeah, so I'll pass it on to Sai for the labeled data sets.
Hello. Thank you, Rohan. Let's move forward about what we mean by labeled context datasets and what experiments we performed on this dataset. Just to brush the concept behind our customized labeled context dataset, let's go back. Let's take two questions here, like why do I worry about your dirty country? And do not ever try making drink milk as I will be angry. Both questions have the same emotion, angry, attached to it, but both have different labels in this dataset. So this is how we customized our labeled context dataset. So what help does this give to us, and what help does this give to an NLP sentiment analysis problem? Let's discuss about that. When we train with no labeled dataset, we found there is no convergence in training accuracy or training loss. But when we train with our customized label context dataset, we found there is a convergence. As you can see in this graph, there is a convergence up to a certain point of time. And this happens once the training got overfit. So with context dataset, we got convergence and we got an accuracy of around 45 to 55%, and it's quite stable. And it's very easy to achieve this as well, unlike the no context dataset. We did experiments on training batch size. We did experiments on how many epochs we have to train and so on. We found that we should train with something around 150 to 200 epochs, as we have to avoid the overfitting problem from this graph. And when we train with various batch sizes, we found better accuracies when we train with batch size of 4. So we fixed this batch size and performed various experiments further. Going ahead, we tested with a couple of neural networks for this customized labeled context dataset. The first neural network is simple LSTM with dropout. The second neural network is LSTM, dropout, and skip connections. As you can see in this neural network, we had one skip connection. Training with LSTM with dropout without skip connection had an accuracy of around 40% while validation, and we got around 53% emoji accuracy for this neural network. So when we say emoji accuracy of 50%, it means that for our labeled context dataset, if emotion matches irrespective of the correct label, we say it is correctly classified. Remember that in context dataset, we have labels which are different for the same emotion. So emoji accuracy gives an accuracy without considering whether it is correctly classifying the theme. So for this question of do not ever try making drink milk as I will be angry, will be classified as correct, even if the label is 0 while validation. So that's how the emoji accuracy is calculated. The real accuracy is what we have in our deep learning. If label matches, we have the correct answer. So we have the emoji accuracy of 53% and the real validation accuracy of around 40% for our customized labeled context dataset. And with the next neural network, which has LSTM dropout and skip connections, we achieved an accuracy of around 45% on validation and emoji accuracy of around 53%, which is quite the same even using skip connections. In both of these neural networks, we saw the emoji accuracy consistently being between 45 to 55%. So we took this as a base truth for our next experiments. So let's move forward. Next experiment is about whether giving the context of the question as an input in addition to the question can help achieving even better accuracies, better than 55% that we achieved in the previous slide. And it seems that our gut feeling is correct. We achieved better accuracies by giving this context as an additional input along with the question. Our thought behind this experiment is to make our neural network train more on the emotions and not on the theme or context of the question, which means our thought is to make the neural network training as context or theme independent. So here comes the concept of context independence, which we like to introduce, and it is a proposal from our project. We will go over how we implemented this concept in various forms in the next slides and how performance metrics are for this concept. So here is our solution architecture. Along with the question, we give the theme of the question as an input, and we achieved an emoji accuracy of around 65 to 70% on validation. And here is our first implementation. We give the context as an input in this manner. Let's take a question, why do I worry about your dirty country? We give place in addition to the question as well as an input. With this, we achieved a validation accuracy of around 60% and emoji accuracy of around 64%, including some spikes of to around 70% in some runs. This performed better than our earlier case, which we did not give the context as an input to our training. So let's go to the second implementation. Here in this implementation, instead of passing the context along with the question, like in the first implementation, we designed the loss function, which could remove the dependency on context while training. The custom loss function will hard code the loss as 0 if emotion matches for a data point, irrespective of the theme, while training. With this implementation, we saw better emoji accuracy, though the validation or real accuracy remained poor. The reasoning behind this better accuracy is better articulated, and it makes better sense when we think in terms of how training happens. When loss is 0, there will not be any update on weights and it stays same. It may give poor validation accuracy due to unmatched labels, but give better emoji accuracy with matched emotions. So we see the validation accuracy coming around 45 to 50% and emoji accuracy of around 65%. So on conclusion, we would like to present our proposal, which is about building a two-stage neural network for better sentiment analysis. Thus, we show the sentiment analysis better done with context or theme as input. Here's a demo for all of the 4 experiments performed on our customized label context dataset. First experiment, just a summary of what we have gone through. The first experiment is on LSTM based, no slip connection, and no input on the lines of context. We achieved an accuracy of around 45 to 50%. Second experiment is with LSTM with skip connections. Accuracy is 45 to 50%. The third experiment is LSTM based with custom loss function to make context or theme independent. We achieved a training accuracy of around, we achieved a validation accuracy of around 55 to 65% on training. The fourth experiment is LSTM based plus input context to make context or theme independent training. Accuracy we achieved is around 60 to 70%. All of them we mentioned is about emoji accuracy. So here is our demo videos for all of the 4 experiments. Let's go to the one which we got the higher accuracy, which is when we gave context as input along with the question, why do you worry about your dirty country? We also included place as an input. Let's forward. Yeah, so we achieved an accuracy of around 67% now with validation accuracy of around 60%. So giving the context as an input performs better for sentiment analysis, and this is our proposal from our project. And thank you for listening. Thank you.